All right, shut up. Today we're going to get started with the bread and butter of geophysics, at least as it applies to petroleum geology. And in preparation of that, I'm going to start hanging these things up periodically. This is available online. You can download it. I'm going to see if I can blow it up into a larger format to print it up as a large chart. This is the Atlas of log responses. Sounds impressive, doesn't it? It's basically how different electric logs respond to different formation parameters. And we'll start talking about how this all works a little bit later on today. So by the time we're done with this part of the course, you'll be introduced to all of the major types of electric logs that are used in the petroleum industry, and we're going to focus in on some of them as they apply to interpreting different subsurface geologies. Now that's part of this week's lab exercises, and what we're going to start doing now is getting into lab exercises that are going to build up on each other. So this week you're going to be doing a lot of log correlations. I'm going to warn you now, there is a significant amount of work you have to do just to get ready with things. Electric logs, when you get them raw, tend to be really long things. They roll out and basically like toilet paper, and we do not have the facilities to duplicate those things. So basically what we do is we put them onto pages and you glue them together. So there'll be plenty of scissors and tape for you to do this, okay? So be prepared to go back to coloring 101. In addition, in case you are not aware that every Halloween we have different organizations doing things that are pretty good service-wise, if you look at the bottom of the attendance sheet as it goes by today, you'll see that there is a bonus opportunity in this class. The USA Honor Society is doing a can drive, and basically every Halloween what they do is they go from neighborhood to neighborhood raising cans or getting cans for the area food bank. It's a very important thing. I really approve of this, especially now. It's pre-Thanksgiving, and right now the coffers of the food bank are virtually empty because nobody thinks to donate until just before Thanksgiving, where everybody asks for cans. So the deal is going to be, I will give 0.1% per can that you bring in by Friday at noon. Drop them off in the office. There will be a drop-off box there for you, okay? This offer will be reproduced for all my other classes as well, okay? I don't want you to start relying on bonuses by which to pad your grades, so I'm going to put it as a 10-can limit. That means you can get 1% extra credit for this. There'll be a sign-up sheet. Drop the cans off in the office. I don't care what they are, as long as they are not expired, okay? Stop playing the game that so many people do, is that they have stuff lying around, they just throw them out from home. Don't do that. Okay, it's a good service. All right. If you are in my Geology 302 class, and some of you are in Geology 302, then I'll apply the same offer to you. Okay, but it'll be an additional 10 cans for that class. All right. You can't piggy bank things. Okay. So anyway, if you are interested, make sure you get that stuff by Friday at noon. And there's only so many beans that people can handle. All right, so vary it a little bit. Cans of soup, maybe. You know how it works and all that. All right. Okay, so let's get started. You can kill that now, and we're going to start talking about electric logs. Now, if I'm not mistaken, Connors has already talked a little bit about some of these things, but I'm going to start talking to you a little bit about how they have applications to the petroleum industry. Today what we're going to do is look at two of these logs, the so-called SP and the resistivity logs. And the reason why we're talking about these things together is that they are routinely, or for the most part, tend to be run in parallel. So you end up getting these strips that look like this. So what you're looking at here on the left-hand side, this is the SP response to downhole depth. So depth down through here, SP on this side, and this is resistivity. And there are multiple resistivity scales that are normally overlapping on this. This is a nice cleaned up version of things. Now I've said this before, this is the bread and butter of petroleum exploration geology. Not the geophysics in the sense that you'd be looking at seismic lines, but if you're going to be working in an oil company in their exploration division, if you're working in a field trying to find out where to drill new wells, or evaluating the parameters of reservoirs in that particular region, you have to get really familiar with these things in a hurry. And in this class, there's no way I can go over all the detail that you need to do. When you work for an oil company, they will send you away to do short courses, multiple short courses. Some of those short courses will just be on one log. And you're going to learn more mathematics than you ever cared to do. Because a lot of times they use these logs to determine things like the percentage of water to oil or the formation salinity, all manner of things, okay? So we don't have time to do that. What I want to do is just get enough stuff under your belt so that you can do the interpretive exercises in lab this Thursday, all right? And start to appreciate just how useful this is for doing everything from mapping subsurface formations to determining where they go and ultimately where to look for oil, etc. Okay. Now, before we do this, last time we met we were talking about petroleum geology. This was the last of our lectures talking about basically background information. We talked about reservoirs, we talked about trapping mechanisms, and we talked about the porosity of various walls. And as you see, porosity is going to be an important parameter in today's discussion as well. We talked about the reservoirs themselves, and they're almost always going to be sedimentary in nature, which is why if you're going to be a petroleum geologist, you better get as much sedimentology under your belt as possible. Understand the rocks meticulously, then you can start looking for variations and start looking for the exceptions to the rule. And again, porosity and permeability. That's why many of the logs we're going to start talking about are actually used as porosity evaluators, or in some cases, as you'll see today, permeability as well. We talked about the trapping mechanisms, and here's where actually geophysics in terms of seismology is often more relevant than actually doing the logs, because you can actually pick up subsurface pictures like this, provided, as you will see, that you have enough thickness and enough variability across the different rock types. That is the great limiter in terms of geophysical interpretation. If the rocks don't give you what you need, you're not going to see what you want to see. And that's a real problem, because sometimes, as I said, you just don't get what you want. And then we talked about porosity, we talked about primary porosity, secondary porosity. By now, most of you have had a chance to look at most of the thin sections, one hopes. And for those of you who have not done this yet, I want to remind you, labs are not things that are due 3 weeks later. I want these labs in at the start of the lab period this week, because you don't have time to be stuffing around. So if you're planning on working on this during Thursday's lab, you're going to find yourself in big trouble. In fact, I should mention too that the due dates have now been added to the web page, and you'll see that all the due dates for all the labs are the Thursday of the lab period at the start of class, not at the end, not 5 o'clock. Your labs are due at 2 o'clock. So if you don't already have them done, make sure you get them done, okay? And be in this classroom at 2 o'clock on Thursday, because that's when things get serious. And of course, bring in Band-Aids, because you're going to have paper cuts, and you're going to have to nip your fingers. And we all know how to use scissors, right? Do you need a blunt nose scissors? The little ones? My son has a bunch of those things that are guaranteed not to cut your fingers if you need some. Anyway, this is the important thing, okay? Understand the different reservoir parameters, okay? So these are properties that everyone has to have an understanding of if you're going to appreciate just how oil gets in and out of rocks, etc. All right, so here's today's agenda. Electric logs, number one. First of all, what we're going to do is have an introduction to the first electric logs. And I'm going to assume that Dr. Connors has gone over some of this stuff, so I'm hoping that for the most part it'll be review, so we can go through it fairly quickly. If it isn't, slow me down, okay? In particular, I'm not going to go over a lot of the math. I'm going to show you what the math is all about, but I don't really talk an awful lot about the mathematics, because to be honest with you, I'm like you. I don't understand it. I don't need to do it. I don't want to do it. I pretend it's not there. But you have to at least understand that it's the things that we're using to model what we're seeing here, okay? And then we're going to be talking about the two logs, starting off with resistivity logs. And again, I assume you've done some things on resistivity. I know you have. And then we're going to talk about spontaneous potential logs, or SP logs, which I don't think you have talked about too much at all yet, okay? All right, so let's talk about electric logs. Electric logs are, in some ways, the only means we have for rapid analysis of the subsurface. Rapid and relatively cheap. Although when you see what's involved in doing this, you're going to think, oh, it's not that cheap. Cheap, not for you, but cheap for oil companies, okay? Remember, they want to get in and out of an area as soon as possible. If they find something that's got oil in it, they want to be able to develop it as quickly as possible, because the longer you're sitting on a reservoir, the less money you're ultimately making. And never, ever underestimate that it's the power of the dollar that really is driving this whole industry, okay? And of course, we need the resources too. The first surface experimentations were exactly what you did in lab when Jim brought out the resistivity meter and we were playing with it over at the well fields, okay? That was done as early as the early 1900s by two French, what would soon be known as geophysicists. Of course, at the time they were doing this, there was no such thing as geophysics specifically, but they eventually would become geophysicists, and they were brothers. Conrad and Marcel Schlumberger. Schlumberger, where have you heard that name before? All right. Schlumberger is one of the three major geophysical support organizations on the planet. The other two are Dresser Atlas and everybody's favorite company, Halliburton. Yeah, Dick Cheney's company, okay? Now, these companies are responsible for doing most of the geophysical analyses, not the interpretation. They basically support the oil companies by doing the logging for them. They give them the data, and then it's up to the geologists within the companies to actually make heads or tails out of those data, okay? So these two people set up their experiments very much like what we did, you know, where you basically have meters along the surface and ran things to the depth to see what kind of changes were taking place at depth. Now, when they were doing this, oil exploration was still in its infancy. The first oil wells were drilled in the middle to late 1800s. And by the way, does anybody know where the first oil well was drilled? And I put $5 on it, says you don't know.
In the Gulf of Mexico.
Sorry? No. Nope. Southern Ontario in Canada. A place called Saltina, if you can believe it or not. Yeah, this was really, I didn't realize, but you drive down the road and they have the big plaque up there saying this is the first oil well. Now, those oil wells, before you get really excited, were drilled in areas where there were oil seeps at the surface. Pennsylvania followed soon afterwards, by the way. They were drilled down using rotary drill devices, using steel cutting tips. They'd go down maybe 100 or 200 feet, and that was about the maximum depth they could go down through. Okay, now technology, as time caught on, developed harder materials, more powerful drills. The steam engine was replaced by the gasoline diesel engine. You get the idea that we could go deeper and deeper and deeper, and indeed we still do that now. But you can see the problem here now. If you're trying to figure out what's below the surface, no matter how deep you're going, you're stuck. You got a hole maybe that big trying to figure out what's below the surface. Now, this first attempt to measure resistivity was a clever way of trying to determine what the nature of the rocks were before, because there's a simple assumption that if you have a rock that has a changing resistivity, it probably means it's a different material. So you would look for those things that either had zero resistivity or a lot of resistivity, depending upon what you're looking for. And if there's a sudden change, that would mean that there was a formation contact somewhere below the surface. And after a while, you'd start to learn where the shales were and where the sandstones were, etc. But you did this. You know what a pain in the ass this is. It doesn't actually allow you to see vertical changes. You have to be lucky. You have to know what the spacing is in order to determine what's below the surface, or alternatively, when you see there's a transition, you drill down that far and you might be halfway through the reservoir, you might be at the very top of the reservoir. You don't have the control. So what Marcel and Conrad figured out was, why not take this into a vertical dimension? And what they did was, they came up with the first attempt to do this in a vertical nature, and they did it in 1927. All right? This is a celebrated day. What they did here was, they basically took those resistivity things and put it on the end of a line and dropped it down the bottom of a hole. And this particular one, you know, I can't even read the depths on this, but this is their original log, and you can see it's still very primitive. They still had to measure the data at these various points down through here. But now what they could do was they could stop and control it. Now, what we've done from the time they first did this is to more or less make it automatic. Instead of having the readings manually determined, we have the devices that can do it continuously. So it's a continuous measurement of various electrical properties. Yes, sir?
Was the same stuff with 4 pieces on one straight down?
I don't know exactly how they did. I suspect what they ended up doing was having, rather than 4 of them, having 2 devices where there'd be one as a receiver, one as a transmitter. And then what they would do is they pull it up together, all right, and then they would stop periodically, and at the top would be, again, a gauge. So what they would do is they would measure it. In fact, they may have actually had the ability to see the needle swinging back and forth as they went up, stopping whenever they wanted to. I don't know, because again, this was an experiment more than anything else. All right? But I do know that what we do now is completely separate. We don't have measurements periodically. It's a continuous measurement. Now here's what we do today. It's gone a long way. Companies like Schlumberger, Dresser Atlas, or Halliburton, anyone you want to look at, have everything packaged up in really nice little bundles. So when you start drilling, all right, and you're drilling your hole down, once you get down to the bottom of your depth, what you do through your blow-up protector is that you can now start to access that hole. So what you need to do is be able to run your probes down from the top of the hole down to the bottom, or usually what they do is they drop it right down to the bottom and then they raise it back up, okay, in terms of stuff, okay, and then they give the responses according to what the depth is. So trucks like this have all the computer equipment in them, they've got all the their measurement devices in them, and depending upon where you are, they'll either bring it out to you in a truck, or they'll put it out on the back of a container and take it out by barge, or take it out by a pilot boat out to the offshore rigs and set up everything there. It's, as I said, very well contained. By the way, I went out to Mississippi this weekend to visit with my my family, and I was amazed by how many rigs are operating in this area now. I passed 3 active rigs between here and Natchez, Mississippi, so they're doing a lot of drilling along the shore, you know, on land right now too. All right, yes, ma'am.
Are they drilling the hole, or is the hole, or is it already drilled?
The ones I was looking at where they were drilling, because they were active. I passed by one at about 12:30 at night. It was all lit up, so they're drilling.
I think that's Schlumberger truck here.
I'm sorry. What is?
Are they showing up to a pre-drilled well and then dropping?
Well, I'm showing you. I just took this off the internet, so that's a picture of a well. I don't know what state of completion it's in now. So these are not related pictures at all. All right, so they'll continue to drill. The rig will still be up while they're running their probes, because as you'll see, the probes that they use actually have to take advantage of the derrick capacity. And you all know how these things work? I actually haven't told you anything about. All right. Well, basically, they have a rotating platform at the bottom here. That's where most of this is diesel engines to run the turret. Okay, so it turns. It's got a clamping device that clamps, and as it's turning, it's forcibly causing the drill pipe with the bit on the end to turn. They add drill pipe to the top here. There's a little crane off the side where they can actually grab stacks of pipe, bring it over here, load it up. That's what the roughneckers do. Okay, and all right, at the end of each pipe, there's 2 threads, a male and a female, and don't quote me on which one is which, but I believe it's the female thread is at the up end, and then the male thread is the insert end. And basically what they do, as this is turning, they bring these pipes that are suspended by a chain on the side here. All right, so that's the one that's going into the ground through the turret here that's turning, and it's turning at a fixed rate. I don't know what the speed is or anything like that. And what they do is they position the next pipe as they're getting to a certain level below it, they more or less just put chains around it to guide it down. And then what they do is they will put the male thread, they'll catch it here, it will tighten up, and then you're supposed to let go of the chain. In fact, the difference between a good rough-necker and a bad rough-necker can be determined on a handshake. Good rough-neckers shake like this, bad rough-neckers shake like that. Okay? Because if you don't get your fingers out of the chain fast enough, you lose your fingers. Now that may have changed too from the time that I was actually watching these guys do this. I mean, we're talking about many, many years ago now, so they may have more automatic systems in doing that. But basically, they just continue to drill down through here. After they're done with it, they pull the pipe out, okay, and just reverse everything out to the side, and then you got a hole in the ground, probably largely full of mud, but you still have a hole in the ground. How do you get your signals out? You need to put a probe down. Now these are the probes. Now, this is cool. This is technology to the extreme. These are a series of different canisters that are attached to make up a composite electron, a well logging device. Now to give you an idea how big these things are, this is from there to there 31 meters high. That's 100 feet. So it's 100 feet suppository that is dropped down to the bottom of the well, hooked up to a cable, and then is pulled up with all of these things recording different things at different times. What they can do on these probes is staggering. This one down here, for example, looks like the base of a rocket. That's a caliper device. What it does is, as it comes up the hole, it will tell you how wide the hole is. The drill bits are consistent in terms of diameter, but when you're drilling through a friable shale, the shale will collapse. So as you're coming up, the calipers will open up, indicating that you have a larger cavern. All right, and then it will shrink back up again. Sometimes the shales will actually surge inwards so that the diameter of the hole is smaller. Caliper readings give you an idea of reservoir consistency. All right, but ignore all that. The main thing to note is that each one of these different devices is doing different things, measuring different signals. And again, it's a matter of efficiency. If you've got a 20,000 foot deep hole, and you want to measure that as quickly as possible to get the data out to the oil companies, get the hell out of there. I mean Schlumberger is trying to make money off of this too, right? You want to make as few holes as possible. To drop one of these things down to the bottom of a 20,000 foot well might take several hours to do that. To pull it up is going to take longer than that, because you've got to give it enough time to actually be doing all these different measurements. Within these things you'll have all manner of stuff, but the most important ones, the ones we're going to focus on in this class, will be resistivity and SP capabilities, which is what we'll talk about shortly, gamma ray, neutron, and sonic density. There are other devices. We can do conductivity, we can do a whole bunch of different things. Different situations may require you to do different measurements. That'll leave to the oil companies when you actually get into them, because they'll tell you more about that and what the interpretations are all about now, okay? But these things are cool. The longest composite device I've seen is 120 meters tall. Sorry, no, 120 feet tall, not 120 meters tall, okay? 120 feet, which is pretty stunning if you think about it, okay? And here's what you get. Okay, and these are multiple things all side by side. So here's an SP log, there's resistivity, there's sonic, there's neutron processing. They use this actually for determining bulk density of rocks. We'll talk about the applications of each of these as we get through it. In fact, we'll talk about sonic and neutron properties, I believe, in our next meeting on Wednesday, okay? So just a bunch of squiggly lines. But what the Schlumbergers did in 1927 was to more or less actually have to manually read these things as they came up. Now, as I said, this thing is just automatically recorded as you go up, pulling it up, taking various devices, and there'll be all sorts of reading devices depending upon which probe you're actually using at any one time, okay? And don't ask me if they're mutually interfering. I suspect in some cases there are some problems with that, but they've been thinking about this a long time. So if you're trying to measure resistivity in one direction or one point, you're going to have resistivity at one point while you've got conductivity at another, okay? So, all right, so how does resistivity work? And again, so you guys have talked about resistivity with Connors, right? All right, so you know basically we're talking about a simple electrical relationship governed by Ohm's law, where E equals IR. And I'm not sure if he gave you the exact parameters I use here. This is from Schlumberger's website, I believe, where E is the potential in volts, I is the current in amps, and R is the resistivity. And here you can actually see that they got some numbers on this. Actually, this has nothing to do with resistivity, but it shows you that basically different rock units are going to have different numbers associated with them, okay? Resistivity itself, all right, is a property that measures essentially the resistance of a formation to a current applied to it. And it's measured in terms of ohm meters squared per meter, which is reduced to ohm meters. But the important thing to note here is that we are measuring things over an area, hence the ohm meters squared per meter. So a lot of times when you just see this, you don't really appreciate that this is an area measurement. Certainly the area is factored into the formula, okay? So the resistivity is equal to R times the area divided by L, which is the length of the separation between the two probes you're dealing with, okay? And that will be dependent upon what kind of probe you're actually using in the that Schlumberger happens to be using. And conductivity in this case can be just taken as the resistivity, but as the reciprocal of the resistivity and all. Although, as I said, I've seen them measure them separately in some of these devices as well, okay? Now, parameters to worry about. And again, here's where you do have to be very careful about things, okay? Because you cannot assume that the numbers you're getting are absolutely the numbers that are there. Resistivity is going to be dependent upon the properties of the fluids as well as a few other variables. But you have to remember that when you make the well, when you're drilling the well, there is going to be the potential for modifying the signal. So you have to be really careful about this. Now this diagram, this is a classic diagram that all of you are going to see if and when you get into the oil industry. What it's showing you is your borehole, and that's the drill hole through here. You have shale on either side of a porous, permeable bed. No one is saying whether it's got oil in it or what, okay? But if it's porous and permeable, it's going to have a fluid in it of some sort, probably water, possibly saline water. The thing to note is that when you're drilling down through this formation, you're going to be drilling under pressure, and that pressure is going to be generated by a combination of the fluid that you are bringing down to saturate the mud, which is used both as a lubricant, as a means by which, and also means by which to control the pressure of the formation. You don't want a blowout. Everyone knows that blowouts are bad, especially what happened this past summer. All right, if you have an uncontrollable blowout with oil or whatever water pressure is surging upwards, you lose control of the well and you're up a creek without a paddle. All right, what you want to do is provide enough pressure so that what you do is keep the pressure of the formation from escaping. But to do that requires you to add pressure of your own, which is done by a combination of mud and fluid. The problem with that, from a point of view of understanding what the formation is all about, is that you're going to start having some of that pressure entering into your formations at the various places that you don't want them to, the porous and permeable units. So this diagram is showing you more or less the problems you have to deal with when you're trying to unravel or understand formation properties. Along the margins of the hole are going to be what they call the mud cake. This is the area where you literally coat the surface with a layer of drilling mud that is, I think everyone can appreciate this, that's going to be stuck there because it's going to be lining the entire hole all the way down. That mud cake is essentially like pottery clay. Okay? It's thick, slimy. But you're also going to have some problems where you start having the formation itself affected by the pressure of the that you're exerting down the hole. There's the so-called flush zone where you actually take whatever formation fluids happen to be there and push them away from that interval. Okay, so you flush it out and replace it with your own fluids. There'll be the transition zone, and then you're in the uninvaded zone. What you really want is this, because that's what you're trying to measure. But you've got to overcome this problem. Now, how wide that interval is really dependent upon the porosity, the permeability, and the contrast in pressures between what you're applying and what is actually there. So we have developed different devices that can allow you to actually look at the short range resistivity and the long range resistivity, as well as other parameters. And sometimes that is useful. For example, if you've got a short range resistivity that is showing you a kick like this, and the long range is doing this, by looking at the differences, you can get a little bit of an idea of things like reservoir pressures as well as porosity permeability. So there is sometimes an advantage to having this component to it. But for the most part, that interval in through there is a problem because you're changing the properties of the formation. Okay? Now, this diagram is applicable to virtually all types of induction or lateral log type of applications where you're applying a current and trying to see the responses. All right, it's not always a problem in some other applications, but certainly for SP and resistivity it is. Okay. All right, so then I mentioned the shallow versus deep induction, and here basically is where you see one of those logs. Now this one is opposite gamma ray through here. You always see resistivity is always the wide range on the right-hand side of your logs. They are either paralleled with SP on one side in resistivity or gamma ray on one side in resistivity, okay? And here you're going to see shallow versus deep resistance. By the way, I should also point out that resistivity is something that is extremely variable. I'll give you some numbers in just a second here. So the scale that we use here is by necessity logarithmic. And you'll see multiple scales here depending upon which one you're actually looking at. This one has two. Medium induction, deep induction, indicated by the different lines. Actually, three. 1, 2, and 3. Solid line, light dashed line, heavy dashed line, and they're all overlapping here. In the good old days, What you got was a paper printout, and that was all. Nowadays, everything is digitized almost immediately, color coordinated, and you push a button, you can get rid of the ones you don't actually want, okay? So things are a little bit different now in the real world compared to what we're teaching you here. But still, when you're looking at applications, you can see that, you know, sometimes you have to deal with this. And indeed, there are some wells that you're going to be having to deal with that only have old paper logs, in which case you're still going to have to be able to interpret something like this. And I mentioned I was going to give you some resistivities, and here they are in terms of different fluids and different materials. Oil is a very resistant material. Its natural resistance is 1 × 10⁸ ohm meters. Fresh water is significantly more conductive, so it's down there. Seawater, salt water is far less than that. All right, and then you'll see clays are variable depending upon what they actually have in them. As far as the rocks go, quartz, calcite, dolomite, the major components that are hosts, all have about the same resistivity. In other words, the same as oil. They are basically insulators. So in many cases, we can ignore them entirely. All right, so we don't have to worry about them. And so when you start seeing these differences in resistivity, they are largely associated with the fluids that are in them. But obviously, it stands to reason that it's also going to take into account other things like the porosity, etc. too. Okay, so that's why we were talking about porosity earlier. All right, so other important things. Did Connors go over the Archie equation for you? It's a buzzword. It's one of those things that when you actually go to do an interview with somebody, they're going to talk to you and they're going to say, like, how familiar are you with things like the Archie equation? My advice to you is when you get an interview saying, like, well, we talked about it in my geophysical class naturally, but we didn't spend a lot of time on it. That's the safest way of saying, I heard of it, but don't ask me anything more about it because I can't bluff anymore. All right? But if you go to an interview and say, like, I don't know what's that, then you're basically going to be bumped down to the bottom, okay? So the rules are, you go to an interview, have a hand lens in your pocket in case someone gives you the terrible question of, do you know what kind of rock this is? All right? And also know some of the buzz expressions, enough to more or less acknowledge you have some experience on that, okay? Anyway, so this is the Archie equation, which is more or less expressing things like the resistivity of fluids over the porosity, and this is the important thing, all right? That's the porosity that's controlling things, and that M there is, I call it a fudge factor. It's a cementation factor, more or less is allowing you to kind of factor in things like permeability and porosity. As far as I understand, a lot of these relationships, whether it's like Darcy's law for hydrogeology or the Archie equation like this, a lot of these things are not easy to model. Basically what you do is you determine the parameters after you've actually started doing some detailed interpretations. You come up with the fudge factor after you already know what the relationship is, and then you take that fudge factor and apply it to similar situations to more or less model what you think is going to happen. That's the same thing as I said, with the Darcy's law of relationship in hydrogeology. All right, so here's the important thing, okay? What controls resistivity? It's going to be the salinity of the formation, pore water. All right, and that means if you're dealing with oil, of course, there's going to be no salinity associated with it. It's going to be the volume of the pore space, the geometry of the pore space, okay? That's why we did lab number 2B like we were doing last week, as well as things like the temperature, the types of clays, and the various phases of the pore fluids. Now these are a lot of variables, and in petroleum geology we don't like to have to model a lot of things independently, so there are a series of tables that you can use. They're called correction tables. If you know what the temperature of your formation is, for example, and you know what the salinity is, you can put a fudge factor into your calculations by simply following a couple charts. Those charts more or less make up the entire volumes of the Schlumberger log interpretation courses or the Dresser Atlas log interpretation courses. I will bring a couple of those things in for you to play around with in lab this Thursday so you can see how they work, okay? So basically what you need to know are things like formation temperature and salinity, and it will tell you how to modify things like the resistivity to take into account some of these variables. Now, let's turn our attention to spontaneous potential logs. You know, I always have problems explaining this one. Resistivity is easy. Spontaneous potential, or self-potential, and some people even call this the shale potential logs, is a real bugger to try and explain how this actually works, okay? Essentially what this is you're looking at the difference in potential from an electrode placed at the surface to an electrode that is in the well at some point. So this is a comparison in terms of potential for the conductivity of electricity, okay? So at the stake at the surface you have a copper stake, and I assume they have a wire that's hooked up to this that is linked to the SP sonde within the probing device. And I haven't actually given you that term before. I better mention that before I start using it. The sonde is the actual logging device, okay? So there's different components to it that they have in there. All right? Now this diagram here is more or less showing you how it's measured. As the sonde is dragged up from the bottom, it will be looking at the potential for energy to, from electricity or ion flow to go from the stake down to the formation. And as properties within the formation change, there will be higher or lower potential for this to occur. Now some people refer to this as a battery effect, okay? So down here, this is the battery effect we're talking about. The proper way of defining this, and this is where I get into all sorts of trouble trying to explain it, is the SP results from the IR drop measurable in the borehole produced by the flow of SP currents in the hole. These currents are generated by the electrochemical and electrochemical potentials. And basically what that's meaning is that as the properties change, there's going to be more potential for electricity to flow into the ground at some places or less. The battery effect is how conductive is the material or the fluids within the formation that you're going through, okay? Ultimately, this is being controlled more by permeability than anything else, okay? And that's a key thing. We have means by which to measure permeability and porosity. This one is really quite useful for resolving very dramatic changes in those combinations of things, okay? Actually, you know what? I think I'm missing a slide here. I put a new slide in here to help me explain this a little bit more, and I didn't actually do that, okay? So unfortunately, I cut out the wrong slide actually needed right now. The math involved in SP logs is shown here, and again, I don't go into the detail about this at all, except to say that there's potential, which is the E, okay, that's the thing we're actually measuring. The K is a fudge factor, again controlled by temperature, and then we have resistivities of both the mud filtrate and formation water, okay, so this is just a number that's going to be generated. The main thing to note is that once again you're going to get swings back and forth. The main thing about SP, and this is the first log that I ever had to do in oil servicing, is that it is useful for distinguishing lithology, okay? Admittedly by permeability, but it really is a very quick and dirty device for measuring the different types of lithology, especially sandstones and shales. In fact, that's why they call this, in some cases, the shale potential log. All right, so here we go. We see basically kicks in this direction, then every once in a while we have a kick going off in this direction. You're going to see something identified as the sand line. The sand line is normally taken to be the maximum deflection to the left that you have. The shale line is the maximum deflection you have to the right. So if you know you're in an interval where there's sand and shale, sand kicks out this way, shale kicks back this way, and very quickly you get an idea for where the sands are and where the shales are, okay? I should also point out here that this is measuring the potential for a current to go through the formation. It's dependent upon porosity, permeability, and the ability for ions to actually travel from the well into the formation. You should be realizing that shales often contain an awful lot of water, but the problem with shales is that the water is bound between the plates of the clay minerals. It's very difficult for them to allow for ion exchange. Ions can't pass through shales because the water is bounded together by the clay particles. Not true if you've got open pores with a lot of permeability between them. That's why this is really a really good, useful tool for distinguishing between sandstones and shales. Actually, let me just drop down here for a second, okay? This is one thing you have to be aware of, okay? I mentioned the sand line and the shale line. You have to realize that there's a certain amount of inconsistencies from the bottom of the hole because there's different temperatures, and as you pull up the sand from the bottom up to the top, there will be what they often call some signal drift. It will change in some cases the amount of displacement you get from the sand line to the shale line. And here you can see quite nicely how the shale baseline is shifting in that direction. That doesn't mean that this is less shaly. It means that what's happened is that the signals are kind of drifting a little bit. So if you're dealing with interpreting an entire core or entire hole, then you may have to take into account the idea that the shales at the top may not be as displaced as much as they are at the bottom, or vice versa. Okay, so this shale drift is, or sandline drift, is a bit of a problem. Now, going back here, some other issues you have to be aware of. Okay, here's a nice little SP response to different conditions here and here. When you have got different types of sand beds, if you have nice, big, thick sand beds and shale beds, then what you normally get is pretty good responses in terms of what's happening in terms of kicking. One thing to note is if you have a very thin sand bed, you're not going to see as good of a response because, again, the device actually has its measurements on, it's kind of spaced from one another. So if it's a thin sand bed, you're not going to see it as clearly portrayed as a thick sand bed. That, incidentally, is one of the perils of many of the probing devices we have. So a small little kick like this may be all you're going to get. Also, the amount of shift you're going to get is going to be dependent upon the types of fluids that you have in your rock as well. So here we have a thick, clean gas sand. Here we have a thick, shaly gas sand. Here we have a thick, clean, wet sand. Okay? And what you'll see is that you get more displacement in situations like this than you're going to get for something that has, say, shale in it. So it's a shaly indicator. It can tell you if there's a lot of contaminated sand, but it also gives you an idea of some of the fluids that you have. You also have to be aware that you're going to start having to deal with some issues in terms of changes in the properties of the sandstones as well. If you have more porous intervals, then what will happen is you might get more infiltration of drilling mud. That will change the properties that you're going to get for the SP logs in some cases. The shape of the SP log can be used to interpret what type of formations you're dealing with, as well as starting to think a little bit about how those sandstones were deposited. In other words, the depositional environment. That can be really useful if you don't have cores. Cores are the best way of trying to figure out what kind of rocks you've got because they give you a physical sample. If you can get physical samples of the rocks, you can determine whether it was deposited in a meandering river point bar, or in a deltaic bar, or in a beach. But if you don't have that ability, then you can still get an idea in some cases about what kind of formations you're what kind of depositional environments you're dealing with by looking at the responses to things like the SP log. All right, let me show you what I mean here. All right, so here's these are kind of classic, really idealistic diagrams that people have put together when they're trying to figure out the response to various logs according to what the properties of the rocks are. Okay, so in this case here, let's start off with these two here. Okay, actually, let's start off with this one here because this is the easiest one here. What you're going to see is a series of very thin sand beds that get thicker as time goes on. Moreover, you'll notice that they start off with kind of a minor deflection, and over time they get more and more pronounced in this direction. Then there's a sharp break, and then you're into what would be interpreted as a shale. So in this case, these are interpreted as coarsening upward sequences. Again, you have a mixture of shale and sand here, but as you go up, it gets more and more sand, then all of a sudden there's a sudden transition and you're back into shale, and the whole process repeats itself. But notice, not only do you actually see that jaggedness, but you see the sands getting thicker and thicker and thicker as you go up sequence. This is said to be progradational because what you're dealing with are gradually coarsening upwards, thickening upward sequences. This would be the type of thing that you might expect to see if you're in an area, say like the offshore, where a delta is gradually coming towards your location. So you start off with getting all the mud from the prodeltaic complex, and as you get closer and closer and closer to the site that you're examining, more sand is washed in as mouth bars and meandering river components and stuff. But deltas shift their course very quickly. So you can have sand coming into an area, but if the river changes its direction, all of a sudden you abandon the site that you're looking at, you now start getting mud being deposited again. But eventually what will happen is you're going to have a big thick sand deposit on top of you. Okay? So this type of thing normally is interpreted as approaching delta. And you have to remember, this is the key thing to note. If you're talking about sedimentation within a basin, you're fixed in terms of your spatial location. What's happening is things are shifting towards you as deposition changes. Sea level starts to drop, the delta is going to approach you very quickly. Sea level starts to rise, the delta is going to move back inland. So you're looking now potentially at sequences that are thousands of feet thick, that are representing hundreds of thousands, or in some cases millions of years of time. And ask yourself this: what happens to deposition over the span of time of 100,000 years, or 500,000 years, or 5 million years? Within 5 million years, sea level has done this numerous times. And again, from the point of view of academia, that's fascinating. From the point of view of petroleum, this is a potential reservoir. So is this and this and this, because these are sandstones that are trapped within shales. And while it would be really nice to know how they formed, we want to know how they formed, not because we're academically interested in this. We want to know where one of these things might be 50 miles away. Because when that thing was being deposited here, we know there's sand there. The sand was still being deposited this time, but somewhere else. We want to find out where it was. Okay? So different packages are going to be allowed, be able to be used for interpreting different types of depositional environments, which allows us to model where potential reservoirs are going to be. All right, now with that, yay, finally, I've gotten this down. I've been having a real issue with trying to get the material in an acceptable amount of time. I'm used to 1 hour and 15-minute lectures now. All right, so Wednesday we're talking about gamma ray logs, as well as something, I think it's neutron, I think this weekend. Thursday we start our correlation exercises. It's going to start off with SP correlations. This is the first of what I call your major oil projects. This will be followed by the next week doing the same type of thing, but this time with gamma ray and neutron logs. And then afterwards you're going to take that information and put it together into various types of maps, and you're going to have your first opportunity to make a sales pitch for drilling an oil well. All right? Have fun, kids. Remember what I said about the canned food drive. If you are interested in getting some bonus, hey, even if you don't want the bonus points, why don't you do a good thing? Help contribute to raising food for the area food bank. So bring the cans in by Friday. There will be a box in the office later on today. Make sure you put your name on the sign-up sheet with how many cans you brought in, okay? Lights coming on, everybody blink. Bye-bye.